In this video, we will find out the average, RMS, and peak value of an AC quantity and their relationships. Before that, let's look into the basic terminologies of an AC waveform. Here we consider a sinusoidal waveform and a current quantity. Now, a cycle is one complete set of positive and negative values of alternating quantity. Similarly, a time period is the time taken by the quantity to complete one cycle. Frequency is the number of cycles per second. It is expressed as the reciprocal of time period. Now let's see what is peak value. Peak value is the maximum amplitude obtained by an AC quantity in a cycle. Here, the maximum value in a cycle is at time period pi by 2. If we consider the expression of current as Im sin omega t, Im will be the peak value of current. Now, if we sum the values of current at different time intervals in one cycle and then divide by the number of intervals, we get the average value of current. So, the average value is simply the mean or average of the instantaneous value of the quantity over one cycle. This method is convenient for non-symmetric waves. If we apply the formula in the sinusoid waveform, we get the average value as 0, since the area of the positive half cycle is equal to the area of the negative half cycle. Because the current is flowing to the load and delivering power even in the negative half cycle, the average value cannot be 0. So in the case of sinusoidal waveform, we only consider the half cycle, which will also be the case for symmetric waves. This method of calculation from the waveform is known as mid-ordinate method. The next method uses integral to find the average, which is called analytical method. So if we calculate the area of the half cycle and divide it by the time period, which is pi, as stated earlier, this is for sinusoidal waveform, so we are taking only half cycle. For non-symmetric waves, we should consider area of full cycle when calculating average value. Now let us consider a strip of length d theta with a height of I. The area of the strip will be I d theta. Now for the area of the region, we integrate it with the limit from 0 to pi. We get a solution like this. For average value, we divide this result by the time period and average current is found. The expression for voltage will also be the same. Now, before we see what is an RMS value, we need to know the need for RMS value. We see that for DC waveform, the values are fixed at all instances for any quantity, while in the case for AC, the values keep changing at every instant. So we require a fixed value which can be used to refer the quantities in general, like 10 volt of voltage and 3 amperes of current, which should imply the values are fixed. In other words, we need a fixed value which is a DC equivalent of the AC quantity. Now, if we look into the DC circuit, since the value of voltage and current are fixed, the power can be calculated simply by the formula. While in AC, the value will be different at each instant. So if we calculate power using one value of current and voltage, this may not be true for other instances. This is why we need a single value equivalent to the DC for calculating power. So we need a fixed value of voltage and current to get a value of overall power consumed, which is the factor most are concerned with. Now, if we calculate the power consumed by the load of same magnitude for AC and DC system having same supply voltage, we see that the result is same for both circuits. Hence, RMS value can be defined as the DC equivalent of AC quantity, which produces equal power as the DC value. To find the RMS value, we again use the mid-ordinate and analytical method. Let's look into the mid-ordinate method first. Here we calculate the power at each instant using this formula and take an average of the power consumed. The final expression we find is this value is known as the RMS value, which is also referred as the effective value. If we see the process, we see that first we squared the current, then took the average of the squared quantities, and in the final step, we took the square root to find the effective value. Hence, we get the term root mean square or simply RMS. Now let's look into the analytical method. Previously, we found the expression for average value of current. Now similarly, we find the average value of I squared to find the value of average power dissipated. The process is all the same and we can either take the limit of half cycle or full cycle. While taking the average, the values will be including the negative half cycle as the square will be positive. After calculating, we get an expression of Im divided by root 2, which is the RMS value of current. Similarly, RMS value of voltage will be Vm by root 2. Using the average value and RMS value, we now find form factor and peak factor. The form factor is the ratio of RMS value and average value. Using the expressions we derived, we find it is equal to 1.11. It is significant when comparing two waveforms, with the waveform with higher form factor producing higher hysteresis loss per loop. The next is the peak factor, which is also referred as amplitude factor or crest factor. It is the ratio of peak value and RMS value. We find the value for peak factor is 1.414. The peak factor finds its usage to indicate the electric stress developed in insulating material. Here is a quick recap of the terms and their relationships. I hope you are now clear on the terminologies related to AC waveforms. Please like, share and subscribe and I will see you in the next video.